Today we're going to talk about the wind. Most people understand what wind is. It's when the air moves. Well, we're going to talk about why. And also, you might not realize that wind doesn't just blow horizontally, but it blows vertically as well. So there's up and down movement of the air. And sometimes that can be pretty rapid movement up and down, which is why planes sometimes crash. So let's get into the basics. Why is there wind? Well, if you have an area of air that has a particularly high pressure or high density, and you have other areas of the atmosphere that are low pressure and low density, air is going to go from high to low. All things go from high to low. It's true. Think about it. Water goes from either high elevation to low elevation or high water pressure to low water pressure. Electricity goes from high electropotential to low electropotential. All things go from high to low. And that includes the air. So the air is going from an area of high pressure air to an area of low pressure air, or high density to low density. We can use those interchangeably. If we were to look at that on a weather map, that means the wind is going to go from the H to the L on a weather map. Now it's not going to go straight there because of the Coriolis effect, which we'll talk about another time. But it is going generally from the H toward the L. Now, wind is going to go from high to low pressure because the high pressure air is high density and the low pressure air is low density. And it's going to go from low temperature to high temperature. Now, I know I just said it always goes from high to low, but remember, low temperature air is really high pressure air. If it's a low temperature, it's got a higher density, and if it's got a high temperature, it's got a lower density. So it's still going from high density to low density, but it's low temperature to high temperature. And finally, low humidity to high humidity. You might not realize this. A water molecule or a water vapor molecule actually has a lower atomic weight than an average air molecule, which is usually nitrogen, like N2. So because the water weighs less, it makes the air less dense when there's more water vapor in the air. So dry air is higher density than moist air. Okay, how do we measure the wind? So wind gets measured in two ways. First is speed. The speed for you and I is usually given in miles per hour. If you were in France, it would be in knots per hour. In the United States, for industrial uses, it's measured in knots, which is nautical miles. And if you want to find out what the derivation of what a knot is, I suggest you look it up on Wikipedia because it'll blow your mind. But the conversion is it's 1.15 miles per hour. One knot is 1.15 miles per hour. So generally speaking, you can use them interchangeably. If the wind is blowing 10 knots, it's 11 miles per hour, 11.5 miles per hour. It's measured with something called an anemometer. Now we have two different versions of anemometer. The one on the left is kind of a propeller type anemometer. The wind blows, makes the propeller spin. If you've ever seen like a fan in the window that's not turned on and the wind blows and the fan spins, or a windmill, or a wind turbine, I guess. The one on the right is called a cup anemometer, and it's three little cups that are mounted horizontal, and when the wind blows, it makes it spin. The wind direction is also measured. Now it's measured with something called a wind vane. You may remember old-fashioned wind vanes. Sometimes you'll see these on the tops of barns or garages. It's a rooster, it's a turkey, it's a stagecoach, whatever. When the wind blows, that little rooster is going to turn and it's going to face into the wind. So in this example we have here on the right, the rooster is pointing toward the east, so the wind is coming from the east. We always name a wind by where it is coming from. Always where it is coming from. On the left, we have a different type of wind vane, a more modern wind vane. It's much smaller. It's about the size of a pencil with a big fin on it. The advantage of this type of wind vane is it works much better in a much lower wind. The giant rooster, made of cast iron, needs pretty strong wind to point in the right direction, or very good, very low friction mount. This one is much smaller, much lighter, and it's going to work much better in a lower wind. I have one of these on the roof above my classroom. If you're ever walking down the long hall and you look above my room, Mr. Snyder's room, you can see one up there. And this big thing in the center, you may have seen these along the side of the road. Departments of Transportation in all the states put these up periodically along the highway to measure wind speed direction. I guess not all states, but usually they're doing it to find out if they need to get out there and start plowing the snow. So you'll see these up and down the Northway, you'll see these up and down the Thruway. They're pretty common. Wind direction is generally given in degrees. So northeast is 45 degrees, east is 90 degrees, south is 180 degrees, west 270 degrees, etc. so on. So it's a 360 degree circle with north is 0. Usually it's said as 360 actually. And this is also what we call azimuth. So if you remember when we were talking about azimuth in astronomy, it's the same azimuth, the direction the wind is coming from. So typically where we live, we have a wind out of the west or the southwest, so somewhere between 270 degrees and 235 degrees. The other thing I want to talk about are the global wind belts. Now this is a page in your Earth Science reference table, so you should definitely be aware that it's there and know how to read it. So these belts are the results of vertical winds, and we're going to talk about those vertical winds in a minute, and the Coriolis effect, which turns everything to the right in the northern hemisphere and everything to the left in the southern hemisphere. So let's start where we live. We live at about 43 degrees north, which is right plop smack in that green band in the northern hemisphere labeled westerlies. We live in what we would call the mid-latitude westerlies. And we have a southwesterly wind, generally speaking. If you go south of a line somewhere around South Florida, which is about 30 degrees north, you get into the trade winds. Now the trade winds are generally a northeasterly wind. If you cross the equator, there's southeasterly trade winds, so they're coming from the opposite direction, but they're still easterly winds. And continue on south, you end up with corresponding northwesterly westerlies between 30 and 60 south, and then at both poles you either have northeasterly at the North Pole or southeasterly at the South Pole, easterly polar winds. Let's talk about how these come about. So first of all, at the equator you have the warmest air. Warm air rises. So if we look over here at the equator, you have the warmest air, and that warm air is rising. Does a couple things when it rises. First of all, it makes warm air rise, cool, expand, condense. It makes a lot of rain. So at the equator, it's generally wet. But this rising air is also going to pull air in toward the equator at the surface. So if you look to the north of the equator and to the south of the equator, you have air that is moving toward the equator because the rising air is making a big area of low pressure. And so air is moving from high to low, the low being the equator. At the north and the south pole, you have cold air sinking, cold, dry air sinking, actually. And because of that cool, dry air sinking and reaching the surface, you have air moving away from the poles. You're making a big area of high pressure at each pole. Now, in between, we get what I call the bicycle wheel effect. I'm going to go back and just look at this animation again. If you've ever been riding down the road on your bike and you bump into your friend's back tire, it's a pretty violent jolt. And it's a pretty violent jolt because if you think about your front tire is spinning this way, and it's kind of moving right at the point of contact, it's moving downward. Your friend's back wheel is spinning the same direction, but right at its point of contact, it's actually moving upward. So when the two wheels bump, they're moving in opposite directions, and it makes a pretty violent jolt. You can knock your friend off the bike if you try really hard. Super fun. This is occurring in the Earth's atmosphere as well. So you have the rising air at the equator, and you have the sinking air at the pole, and it creates a little cycle, and then in between, it's creating a third kind of cycle of air. So you have sinking air at 30 degrees north, and then rising air again at 60 degrees north. That vertical motion again causes the sinking air at 60 degrees or 30 degrees north is going to cause air to move away from 30 degrees north. It's causing a surface high. And at 60 degrees north, where the air is rising, you have a low pressure and you have air moving toward it. Now let me go back a slide. So think about the air moving from 30 degrees north toward the equator. Now I need you to turn around. Pretend you're standing at 30 degrees north and facing the equator. So the air, in theory, is going to go directly from 30 degrees north straight toward the equator, except the Coriolis effect, which in the northern hemisphere makes everything turn to the right. So it goes straight toward the equator and then it turns to the right. Now if you imagine yourself standing at 30 degrees north facing the equator, all of these arrows are bending to the right. Now if you turn around and you face north from 30 degrees north, all of those arrows are turning to the right. And if you were to stand at the North Pole and face south, all of those arrows are turning to the right. Similarly, everything is turning to the left in the southern hemisphere. So 30 and you look north, it's turning to the left. If you're at 30 and you look south, it's turning to the left. If you're at the South Pole and you look north, it's turning to the left. So that's what causes the global wind directions that we have. That's it for this video. I'll talk to you in class next time if you have any questions.